Okay, so first of all, thank you, Julia, for the nice introduction and inviting me to give a seminar in the microTAStic. I'm very happy. So I actually just got back from Singapore yesterday, and so I'm now here to give a talk. So I'm pretty glad to be here. So first of all, I just want to introduce so let me just quickly change it to the pointer. Okay, never mind. So first of all, let me just introduce what my background is for those of you who don't know. So I have been working on wearable devices for about 10 years already. I started since my undergraduate back in Berkeley, where I first started to get involved in developing these wearable electrochemical devices. And the very first work was back in UC Berkeley when I was an undergrad, developing this multiplex fully integrated multiplex sensing device where we can detect multiple metabolites, electrolytes together in an integrated format like this one in 2016. And afterward, because that work became quite successful, so we try to expand our wearable devices so they will have more functions. They can detect different things. However, we realized that even we are developing all these different types of devices, it's just quite difficult to be realized in practical scenarios. So as an independent PI right now at HKUST, we wanted to focus more on not just expanding these functionalities of these wearable devices, but more on trying to tackle these specific limitations that we are facing currently right now to push those wearable devices into practical scenarios, especially in the aspects of the chemical sensing as part. So the goal here in our lab is we develop all these different kinds of wearable devices so we can collect those individual health data. So in case if there is something happen, those wearable will be able to provide us more more signals that we won't be able to even know ourselves. So we can get those data timely manner, and eventually by collaborating together with the physicians and also using machine learning assisted data analytics, we can actually identify those features and we'll be able to timely tell us if we are in good health condition. Right. But right now, because those commercial devices are mainly focuses on the vital activities, but not much on the chemical sensors. So for the chemical sensors, we will typically see continuous glucose monitor. That is the only one that is widely available for the diabetic patients right now. So if we want to have more applications and want to detect more molecular information, it's quite important for us to do so, to have those different chemical sensors. So in my lab, we are actually developing more on the electrochemical sensors. So for the electrochemistry, it's quite simple because we are pretty much looking at all these ion or electrochemical electrochemical processes and trying to monitor these voltage or current that arises because of these different processes, right? So in here, I have like a simple electrochemical setup where it is supposed to be electrochemical cells pretty much to generate electricity. But here, I'm just showing that we can have it for the sensor as well by having one as the sensing electrode or working electrode, we usually will say, or the other one as a reference electrode, or we can also have 3 electrodes where the third electrode is going to become a counter electrode. And our typical electrolyte solution will become our sample. That's how the electrochemical sensor is. But right now, if we look at how these electrochemical sensors are utilized in the clinical settings, so here are a few things that I could find. And you will see that for the at the clinical level, we have these electrolyte analyzer where we can monitor, for example, our potassium levels if we are at the within the very narrow range. Also, like for the dental caries pH monitor to monitor our tooth health, or also like the very typical glucose meter that we can actually buy at a convenience store, and eventually the continuous glucose monitor where we will be able to continuously monitor our interstitial fluid glucose level for a long term. So these are quite a few these are all based on electrochemical readout. So, but then you will see that these are just the commercial sensors we can find and usually practice at the clinical settings, but we cannot really expand much. That is because it's quite difficult to expand those electrochemical sensors especially in the wearable settings. And so now I will go through which are some of the limitations that we are facing right now. So to know about the limitations in the electrochemical sensors for the wearables, I just want to briefly start introducing how electrochemical sensor usually works. So this is a typical the process of the fully integrated device for the electrochemical sensing, where we will have the sample and the sample at the top, and where that sample will be actually interfacing with our porous membrane, where that porous membrane will contain the biorecognition elements. So if we look at it at a more larger view, we will see that these little pink ones are the biorecognition elements. So when these analytes in the sample start to come through the porous membrane and interact with those biorecognition elements, there are actually a few things can happen. For example, there can be some ion exchange going on, or maybe because of the interaction, there may be some electron transfer going on. So if we use this as the working electrode and we can make it into a closed circuit by having another reference and counter electrode where both of them are all immersed together into the sample, then we will have that closed circuit so we can capture those electrochemical signals, including the voltage of the potential and the current. So then now let's just look at a little bit more into details of the problems that we have. For different electrochemical sensors, actually there are different problems. So we cannot actually commonly say, oh, the problems exist for all of these sensors. So that's why I just pick up an example of the commonly reported sensors in wearables here. So typically for the electrochemical sensors used in wearables, it will look something like this, where we have multiple functional layers. And these functional layers, they have their different capabilities. One is, of course, to recognize our analyte specifically, and the others are usually the mediator to help with the electron transfer or to change the ion signal into electron signals. So we have all these multiple functional layers, right? So when we have those sensors fabricated, usually these functional layers can start to do something when we are testing inside the sample. So these includes, like, for example, those species that we don't really want inside our sensor can start to interfere. And it will actually lead to the signals that is really not really accurately reflecting what we really want to measure, which is the analyte signals. And also another possible thing is that after we put them into the sample for some time, especially in a wearable, there are possibilities that they will start to swell. So when these functional layers have their own different properties, they can start to delaminate as well, and it will also interfere with the sensor signals. So then what we are aiming to do is that can we avoid these kind of problems or try to minimize those problems, especially we don't want those unwanted species to be interfere with our signals, as well as those interfaces that is really having the delamination problems. So we will not have those erratic signals in the end, right? So that is pretty much the one example of the problem that we are facing right now in the electrochemical sensors. However, there are more to it in the wearable device, because like the previous challenges that I mentioned, they are actually, you can say these kind of problems exist even for the point of care device. However, it is a little bit easier to tackle because because they are only for one-time measurement, right? But for the wearable, we are actually aiming at for a longer term measurement. Even it can be like every second, every minute, or every hour, it doesn't matter, but it's supposed to last for a long term, right? So then it has more problems. So again, just to give an example, that is based on potentiometric readout-based biosensors like electrolytes analyzer. So even though electrolytes analyzer seems like, oh, we can only detect electrolytes. However, what I'm saying here is for the potentiometric readout base, there are actually many different types of biosensors are possible. Even for metabolites, there are potentiometric readout based sensors as well, right? So we are just saying in general, for those with potentiometric readout based transaction, we have what I have in the illustration here, we have a few problems. So usually when we have the sensor fabricated, there are a few things we need to do even before we start to capture those our on-body data. So for example, what's going to happen is after we have those sensors, at the user end, what we need to do is that first we need to stabilize the signal of our sensors. That is, we usually will say that we have to do conditioning process first, so the sensor will go from unstable signal to stable signals. And after the sensor reach a stable signal, we have to further do is that we have to normalize the baseline. That is because for all the sensors, they have their own baseline. So if we don't do normalizing, we can have we will have problem in translating the signals into the respective analyte concentration, right? So we have to normalize the baseline, which is typically the commonly seen in many of the sensors, even in the pH meter, right? So they all will add up to the turnaround time for the users, and which can take hours or even days. In the worst case. So it's actually not that good, right? So we don't really want to have those process for the users because for the users, the convenience is the most important thing for them, right? So we want to eliminate that process so that once the sensor is fabricated and delivered to users, the user can directly wear it and immediately will give out some signals, and those signals will be readily translated into some specific concentration of the analyte that we are trying to look at. So for that, we need to achieve something that is listed here, which is including like the sensor has to be stable, has to provide uniform performance, as well as should be able to give more immediate measurements for the ease of use at the end of the users. So to achieve this, again, focus on the electrolytes analyzer. This is just the cross-sectional version of what I have shown before, where we have those electrolytes analyzer usually contain multiple functional layers. So it looks something like this. So in the electrolytes analyzer, usually we are looking at these electrolytes, and these electrolyte signal come from the ion exchange process. And this ion exchange process will actually lead to the change in the voltage, which is the open circuit voltage we are trying to look at. But in this kind of sensor, the most detrimental effect is actually the water. So we don't really like water much coming in. So, but for the typical electrolytes analyzer, what we usually see is that there is some hydrophilic surfaces in these functional membranes. And also the incompatibility of these functional membranes will lead to the sharp interfaces. So eventually, when we put it into our sample, put the sensor into our samples, these electrolytes can actually come in, but the waters will also flow in a large amount. And at the hydrophilic surface, it can stay more, which is actually interfere with the signals that include the signal will slowly degrade and eventually will lead to failure. So we want to solve this problem by having the functional membranes, functional layers that have more similar properties. For example, everything become more hydrophobic, and also the interfaces become more coherent so that there's no sharp interfaces. So the water will be a little bit more difficult to stay inside compared to the previous case. So with that, what we have been doing is that we are looking at, so traditionally, these functional layers, especially the part that you see here, the second layer, the electrochemical signal transducer, people usually will use PEDOT-PSS based materials. However, PEDOT-PSS is quite hydrophilic. And actually with the ion selective membrane, which is labeled as ISM there, it's not really that compatible because that ISM is quite hydrophobic. So what we are doing is that instead of using P.PSS, which is hydrophilic, we actually change to something that is a lot more hydrophobic, which is P.TFPB. And also inside the ion selective membrane, we also have that TFPB materials added so that the whole thing become a lot more hydrophobic. And also the interface, there is no longer will be sharp interfaces like before that will encourage water to stay inside. So we definitely study a lot of the properties of these functional layers by looking at, for example, their capacitance, their hydrophobicity, because we usually want those the electrochemical signal transducer layer to be very super hydrophobic and also high capacitance. And also because for the wearable, we are leaving it for a long-term measurement, right? So we want to make sure their properties will remain and change over time for a long term, instead of, after we fabricate, the sensors looks good, very hydrophobic, has very high capacitance, but after we test it in sample for maybe 1 hour, it actually lose their properties. That's actually not good, right? So we actually also look at those layers after soaking into these solutions for a long term, how the behavior changes. So we try to come up with the optimal compositions that will have the behavior pretty much unchanged over time, so we can actually use in the wearable device. So in the end, our conclusion is we pretty much have to have those diffusion limiting functional layers with coherent interfaces so that we can achieve these long-term stable biosensors to be used in the wearables. So with this device, we actually are able to achieve highly sensitive sensor, which we can actually reach this inertial limit sensitivity, and also a lot better selectivity and also a lot better stability. So we eventually even tested for about 50 hours continuously, and compared to those traditional ones, which is P.PSS based material, ours can actually last a lot better, a lot more stable. So this part is actually just showing that the sensors can provide these stable signals, right? However, as I mentioned before, there's actually another problem, that is for each individual sensors, even though they may be stable, they actually can give you different signals. That means maybe one sensor give you 200 millivolts, but the other sensor give you 300, another sensor give you 400, then it will be quite difficult that if we want to make it, for example, a calibration-free sensor, right? We have to actually calibrate every single sensor to be able to reflect the real concentration. So our goal is to actually try to minimize so that we can actually achieve a calibration-free sensor. So like before, we look at our previous sensors, how they are, and what is actually causing all those deviation. And what we realize is that, again, it goes back to that electrochemical signal transducing layer. They usually have fast redox kinetics and they don't have well-defined redox potential. That's why they eventually leads to all these different potentials when we fabricate. And other than that, because we are looking at sensor, not just the working electrode itself, but also together as a whole with the counter and the reference electrode. So we have to look at it in the overall picture, how these the whole device can provide a uniform performance or not. So based on that consideration, what we found is that we cannot achieve these uniformly performing sensors just by tuning those electrochemical signal transducer in the working electrode, which has been the more typical ways people have been studying over the past few years. So what we realize is actually we have to include these materials and also engineer the device so that everything come together to achieve this capability of no calibration, no conditioning, and also shelf-stable biosensors. So with that, what we did was we actually used the materials that we have, as I mentioned in the previous few slides. And with that, we have to electrically modulate the biosensor, the whole sensor that includes reference counter and the working electrode, to reach one uniform signal where we actually modulate it to be, which we actually use 0 volt. So with that, even though if we have 100 sensors, for example, we actually tune them all to become 0 volt at a specific concentration where we desire. So eventually, we achieve this type of sensors where initially when those sensors are fabricated in the traditional way, the readings can be quite vary a lot. But with the approach that we have together with including the materials plus the electrical modulation process, we are able to narrow down the variation of these biosensors to actually to become really, really small. And actually, I forgot for the ones that we tested there, I think there are 4 different batches of biosensors. So there are many sensors, and they actually reach really narrow distribution only. And even these distribution actually can remain even when the sensors are tested continuously or when we are having under shelf storage. So they are actually quite good. So we don't have to do calibration at the user end. So eventually, we actually find out for the wearable sensors is under constant motion, the sensors actually won't be that stable. So we actually have a few other materials modification to withstand that as well. But because of the time limit, I'm not going to go through that. So eventually, the device, it looks a little bit complicated, pretty much. With the materials and electrical modulation that I just mentioned. And also there are other little details where we added inside to reach a biosensor where we can robustly collect these electrochemical signals even when the device is used for very heavy physical activities. And what our goal here is, because in Hong Kong, it's really, usually it's hot for maybe like 8 months here. And also there we have a lot of construction workers, and because we also have a lot of mountains, so people love to hike. So for those people, actually, they have the danger of having those heat-related health implications, right? So we actually want to assist them to be able to tell them with our sensors by measuring these electrolytes and also the sweat secretion rate and the temperature to be able to tell when they need to be actually try to rest, so they will not actually push them to the level of, for example, heat stroke, right? So that is one example, and I actually want to give a couple more examples. So another example is we actually use such kind of sensors for the cystic fibrosis diagnosis. So what is cystic fibrosis is that it's just a disease that's actually for those patients, their lungs are actually they have these mucus build up, so they will have difficulty in breathing. And for those patients, their chloride channel is actually impaired. So compared to the healthy people, their chloride level in sweat is actually a lot higher than the healthy people. So typically in the hospital, what is done is that they will actually electrical plus chemically stimulate the very small area on the wrist so that from this small area, sweat will secrete a lot, and this sweat can be collected and further analyzed by using analytical tools. And this process usually will last a little bit over 1 hour in the best case, and it can actually be even longer to actually get the results. However, with the wearable device, we can actually decrease it because we actually integrate the electrical plus chemical stimulation plus the collection and also sensing in one single device. So the whole process can actually minimize down to about 10 minutes. So when I was a PhD student, so we have a collaboration with the Stanford Cystic Fibrosis Center, and we actually look at those healthy people and cystic fibrosis patients with our device, and we can obviously show the difference between these healthy cohorts and the cystic fibrosis patients with the device. And lastly, I just want to mention, so other than what I mentioned about these electrolytes analyzer, we are actually looking at other different types of sensor as well. For example, for levodopa detection. So levodopa is the first-line drug for Parkinson's disease patients. And for the Parkinson's disease patients, for each individual patients, actually they have to have that levodopa, but they have their optimal therapeutic windows. And for different patients, the therapeutic the dosage and the frequency can be different. And within each patient over time, the dosage and frequency will also change as well. So for that, the wearable device can actually be quite useful because the physicians can actually monitor the medication, right? And also can check on if their patients have been in compliance with the medication or not. So with that, we actually developed this levodopa sensor as well. And again, I'm not going to go into detail of it because it's going to become another different type of biosensor. So what I just want to say is for this kind of sensor, there's one problem is because we want to minimize the sensor into very small size. So we start to put them into a microfluidic device. And when we do so, what happens is that the sample amount becomes quite significant, and also the flow rate becomes quite significant. So for example, as I shown here in the plot, the flow rate dependence. So these 100, 300, these values are actually the flow rate in nanoliter per minute. So even these small changes in the flow rates, we can see the sensor signals can change a lot. So we actually cannot ignore that part when we build these kind of wearable device, especially if we are trying to include those small sensors inside these small microfluidic channels. So for that, what we actually did was we actually incorporate a flow rate sensor inside. And how it works is that these flow rate sensors, like the one shown in the straight channels, when we have actually two electrodes, and they have these two electrodes have these interdigitated electrodes coming out. So every time when the fluid start to flow and touch one electrode, we will have those impedance spike, and we'll be able to just count those, and we'll be able to translate them into the volume, and divided by the time where the spike happened, we'll be able to translate them into a flow rate, which eventually we'll be able to use to actually trace back the sensor signals in the end. So with that, we also actually look at these the levodopa signals for. Actually, we are looking at in sweat as well, especially we look at in the natural sweat, because for the natural, because in the natural sweat is actually, it's secreting naturally, right? We don't really have to stimulate like the electrical plus chemical stimulation like in the cystic fibrosis. And also we don't have them to do, because it's the elderly, right? We don't have them to do heavy exercise to make them sweat, right? So the natural sweat is the one that makes the most sense. So we actually look at those natural sweat, and we try to have these levodopa intake and see how the sweat profile evolves. And we actually found that with the levodopa intake, the sweat actually will start to show up these levodopa levels. And the levels actually kind of reflect how much levodopa dosage is inside. So I think it's a very promising area. So we are actually trying to look at into detail a little bit further right now, and hopefully we will be able to use trying to test on the Parkinson's disease patients very soon here in Hong Kong. So in the end, I just want to quickly summarize. We are actually working on these wearable device and also the point of care devices to be able to capture all these different health information. And eventually we want to push forward to collect large data so that with these large data, we'll be able to tell more of our healthy status. So we will be able to push the healthcare to become more preventive instead of being reactive, like mostly like right now. So in the end, yeah, I just want to thank everyone for listening, and also feel free to contact me. I have my email there. So thank you.